Hi, this video will show a short overview of our project. So the project deals with imitating a real arm with a robot arm. So we have a camera here that takes a picture of the robot arm, then the CPU side deals with processing this image and downscales it to a 10x10 image where the pixel values are sent for the FPGA, where we have trained a neural network and the weight from this network is then processed with the input. And then the output of this network will be the specific pose. So we taught the network on 3 different poses, and the output will be one of these 3 poses. Then the CPU side reads this output from the BRAM and then publishes the pose on a ROS topic, where another ROS node is set up to read this pose and control the motors to the desired position. Yes, and now we will show the demonstration of the 3 different poses. So this is one of the poses, and the next pose is this, and then we have the last pose. This is our Vivado block design, where we have the purple or the pink is the neural network, and then the blue one is the BRAM control, where we read the image sent from the CPU and where we put in the calculated pose. And here we have our HLS module with the neural network inference. So this is our testing setup, where we have here the robot arm with the custom printed 3D links. And we have connected to some weight, but otherwise it would tip over because of the shifting center of mass. Here we have the Ultra board with the FPGA and the CPU. And it's also used as a power supply for the Dynamixel motors. Here we have our camera setup. So we have a USB camera here pointing to an image, and it should be noted that the images we use here has not been trained on the network. It is separate images from a dataset. And here we have our ROS setup. So we have some different ROS topics. We have a ROS topic for controlling the motors, and we have a ROS topic for reading the image from the USB camera and then processing it and sending it to the FPGA. Then we have a ROS topic reading the response from the FPGA and calculating joint torques, or joint positions actually. And now we will show a demonstration where we will pick different poses and see what the response of the robot will be. So here we see that it is successfully shifting between the different poses. And it should be noted that the wiggling motion is just because of the system is not being so stiff. And also because of the weight of the robot arm is a bit too much for these small motors. So all in all, it can be seen that we successfully imitated a human arm with a robot arm using a neural network running on an FPGA. So this is a model of our network where we have where we have 100 input corresponding to the 100 pixel values, and then we have 2 hidden layers, and then an output layer with 3 different options for the 3 poses. And now we will show you the downscaled images, which is actually sent for the model. So this is one of the poses where we see it has been made into grayscale and also downsized to 10x10. And this is the second pose and then the last pose. And this is the images sent to the FPGA, which is what is used to decide the robot arm position. And lastly, it should be noted that we are able to overhaul the real-time condition, and the camera is able to record at 30 FPS, and we are able to do all the inference within this time frame.